Children. So I'm back with subjective questions from relation and functions chapter. In my previous video, we had done one marker questions from the same chapter itself, relation and function. Now I'm taking up the three marker problem from the sample paper, which is check whether the relation R in the set Z of integers defined as ordered pairs are a comma b, a plus b is divisible by 2, and we have to show that it is equivalence relation or not. We have to check it, reflexive, symmetric or transitive. We have to check the three types, right? Whether it is reflexive, symmetric or transitive, which we shall do one by one. And also we have to write the equivalence class for the set for the element 0, right? So let us see how we are going to do it. um, Now we will write to check whether R A ordered pairs A comma B, A plus B is divisible by 2 is an equivalence relation. Now first step to check whether a relation is equivalence or not is we will check R is reflexive. And when is any relation reflexive? By the definition of reflexive relation, we know that for R to be reflexive, A comma A belongs to R for all A belonging to Z. Ordered pairs of the type A comma A should belong to R for every A belonging to the set of integers. So how we check that? We consider A plus A, because A comma A will be defined by the expression A plus A. Now when A plus A is written, it is equal to 2A, which being even is divisible by 2, right? 2A. Any number multiplied by 2 is going to be divisible by 2. So all the ordered pairs of the type A comma A will belong to R. So R is reflexive relation. Then what we have is R is symmetric. We need to check it, right? How we are going to check? When is any relation symmetric? For R to be symmetric, for A comma B belonging to R, the ordered pair B comma A should belong to R for all A comma B belonging to Z. This is symbol for all. So consider A comma B belonging to R, belongs to R. When A comma B belongs to relation R, the definition will be applied. A plus B is divisible by 2. We write let A plus B be equal to 2 lambda, where lambda is some integer. Now we have written A plus B in form of some even integer. Since A plus B is 2 lambda, it means B plus A will also be 2 lambda. I can write it like this by commutative property of integers. So lambda belongs to Z. This implies B plus A is divisible by 2 and B comma A belong to R for all A comma B belonging to Z. Therefore R is symmetric. Then we have R is transitive. We need to check that. And again, by the definition of transitive relation, if we have two ordered pairs of the type A comma B belonging to R, B comma C belonging to R, then A comma C belongs to R for all A comma B comma C belongs to Z. So we will take the given part, let A comma B belongs to R and B comma C belong to R. So I have written consider A comma B belongs to R, B comma C belongs to R. By definition of R as given in the question, when A comma B belongs to R, A plus B will be divisible by 2. And similarly, B comma C belongs to R implies B plus C is divisible by 2. I can write A plus B is equal to 2 lambda, where lambda belongs to Z. B plus C can be written as 2 lambda dash, because lambda dash, where lambda dash belongs to Z. So we have expressed A plus B as some even multiple of lambda and B plus C as also even multiple of lambda dash. Now I have to check the expression A plus C. For A comma C to belong to R, ordered pair A comma C will only belong to R when A plus C is equal to some 2 alpha or some multiple of some even multiple of integers, right? Now we will have 2 lambda minus b plus 2 lambda dash minus b from the expression above here. A plus b equal to 2 lambda implies 2 lambda minus b, and c implies 2 lambda dash minus b. From these two I have written the value of a and I have written the value of c. Now when we simplify it, we get 2 lambda plus 2 lambda dash minus 2b. Take 2 common. Inside I will get lambda plus lambda dash minus b. I can assume lambda plus lambda dash minus b as alpha. So it becomes 2 alpha. A plus c is equal to 2 alpha. Alpha belongs to z. This implies a plus c is divisible by 2. इस entire expression को मैंने alpha assume किया है. Now I can see a plus b is equal to some even multiple of alpha. So this implies a plus c belongs to R. A comma b, b comma c belonging to R implies a comma c belongs to R for all a, b, c belonging to Z. So this is my equivalence relation, as R is reflexive, symmetric and transitive. Now what we have to find is, we have to find equivalence relation, equivalence class of element 0. How we are going to find it? We will write it in the definition form first, and we will write equivalence class of 0 is a comma 0. All the elements in Z which are related with 0. So we will write a comma 0, all a which are related with 0, which means a plus 0 is divisible by 2, which means a plus 0 is same as a is divisible by 2. So which integers are divisible by 2? All the multiples of 2 are divisible by 2. So all positive and negative integers, multiples of 2, will be covered in the equivalence class of 0. So 0 including 0, 0, 2, 4, 6 positive multiples, and here negative, minus 2, minus 4, minus 6. So this is equivalence class of 0, and it is carrying a weightage of half marks, this part, and half marks they have given to the proof of the part that R is reflexive. So this question is carrying a weightage of 3 marks. Right? 3 marks, 1 marker type questions were there. This subjective question is of 3 marks. So 3 plus 3, 6 marks. We have discussed 6 marks type questions up till 6 mark portion from the paper. So this is a 3 marker type. Reflexive, proving that R is reflexive, is of half marks, and symmetric part is of 1 marks, transitive part is of 1 marks, and equivalence class of 0 is carries a weightage of half marks. So as I told, relation and function and inverse trigonometric function, they both are comprising of 8 marks. So one 2 marker question which has appeared in the sample paper is this one. Express tan inverse cos x 1 minus sin x, where x lies between minus 3 by 2, pi by 2 in the simplest form. So whenever we have to attempt this type of questions, as I can see tan inverse, and in bracket I have some trigonometric function which I have to simplify. Tan inverse के आगे tan आएगा, then only you will be able to use tan inverse tan x is equal to x. We have this result which we will use in the last step, that tan inverse tan x is equal to x. So my entire purpose is to convert the function in front of tan inverse x in the type tan. हमारा पर्पस रहेगा cos x upon 1 minus sin x को tan की फॉर्म में सिंप्लीफाई करें. So what I do is, in numerator I want this expression to be of the type sin, and in denominator I want expression of the type cos, so that the things can cancel out and I can get something of the type tan or cot. So I can write cos x as sin pi by 2 minus x. In first quadrant, cos x means sin pi pi by 2 minus x. They both are equivalent expressions. Similarly, sin x can be written as cos pi by 2 minus x. Now we have formula that sin a is 2 sin a by 2 cos a by 2, and 1 minus cos a. 1 minus cos a is 2 sin square a by 2. So I will convert this expression in denominator like this: 2 sin square pi by 4 minus x by 2. If this is a, this will be a by 2. Pi by 2 का भी half हो जाएगा और x का भी half हो जाएगा, and you will get 2 sin square pi by 4 minus x by 2. And similarly here I get 2 sin a by 2 cos a by 2, which is 2 sin pi by 2 minus x divided by 2 cos pi by 2 minus x divided by 2. The numerator gets changed like this because it is of the type sin a. It will become 2 sin a by 2 cos a by 2. Now when the things this expression is simplified, we get tan inverse 2 sin this. 2 and 2 are getting cancelled, sin is getting cancelled with sin, and what I get? Cos by sin. So expression now reduces to, simplifies to tan inverse cot pi by 4 minus x by 2. Now cot pi by 4 minus x by 2 can be written in the form of tan pi by 2 minus pi by 4 minus x by 2. This is angle in the first quadrant. In first quadrant, cot pi by 4 minus x by 2 is equivalent as tan pi by 2 minus pi by 4 minus x by 2. Remove the braces sign, simplify, you will get tan inverse tan pi by 4 plus x by 2. And now using the result, tan inverse tan x equal to x, you will get pi by 4 plus x by 2 using this result. So this question is carrying the weightage of 2 marks from inverse trigonometric functions. Now we have discussed questions from relation and functions and inverse trigonometric functions. So keep practicing similar type questions, and I will see you with more problems in my next video. So stay tuned by clicking the like button, and do subscribe my channel by hitting the bell icon so that you are always updated with whatever I post regularly. So see you in my next video. Till then, bye.